Hi scientists, we're going to talk a little bit about pH today. pH is a measure of the concentration of hydrogens in some solution. And this is important because biochemical reactions often deal with gaining or losing a hydrogen ion. And that can affect intermolecular interactions. For example, if we think about the pH scale, pH is the negative log base 10 of the hydrogen ion concentration. And that pH scale runs from 1 to 14, with 1, the low numbers being acidic, and the high numbers being more basic. And the pH of our blood is 7.4. So a change in hydrogen ion concentration can really affect what's going on inside our cells or inside our blood. Let's continue by talking a little bit about water. Water is a pure solution, and at standard temperature and pressure, it can dissociate a little bit into hydrogen ions or protons plus hydroxide ions. It dissociates so little, in fact, that in 1 liter of water, you'll find about 0.000001 moles of hydrogen ions per liter of water. You could rewrite that and say that there's about 10 to the minus 7th molar hydrogen ions in this liter of water. And because the proton came from part of a water molecule, the other part of the water molecule must also be found at a concentration of 10 to the minus 7th molarity. Let's use what we know then about water and its dissociation to think about equilibrium a little bit. Equilibrium is when the products here, or rather the reactants here, water, and the products, protons and hydroxide ions, are stable over time. The concentrations of the products and the reactants are stable over time. These two arrows are equal in size, so there's no change in the two sides of the reaction over time. Given the initial conditions and the KEQ, we can determine the composition of the system at equilibrium. So if we know what's going on over here and the KEQ, we can figure out what equilibrium looks like for this equation. Well, what is KEQ? KEQ tells us the relative amounts of each component, that is the reactants and the products, their relative amounts at equilibrium. KEQ tells us at equilibrium what are the relative amounts of the reactants and the products. So for water, we can write KEQ is equal to those products, proton, and I'm going to raise it to the first power because we have 1 proton, times the concentration of hydroxide ions, again raised to the first power, over the concentration of the products, again raised to the first power. Well, we can fill that in easily enough. We ended up here with 10 to the minus 7th concentration of protons, 10 to the minus 7th concentration of hydroxide ions, and what on earth is the concentration of water? I think that's a really fun question, and we'll be able to solve it. So the formula weight of water is 18 grams per mole. And since for water, a gram of water is actually the definition of a milliliter, we can say that's equal to 18 milliliters per mole. To find out the concentration, I want to know how many moles are in 1 liter of the solution, water. Or we could write it as how many moles are in 1,000 mils. And we know that here we have 1 mole with 18 mils. Let's solve for X. It turns out the concentration of pure water is 55.5 moles per liter, or molarity. What? Okay, we know the concentration of water now, 55.5 molarity. Doing just a little bit of math here, we can solve that Keq for water is equal to 1.8 times 10 to the minus 16th moles per liter. Now remember, that Keq is telling us at equilibrium what will be the relative amounts of our products, the proton and the hydroxide ion, compared to our reactants, pure water. You can see that this number is very, very small, and that makes sense because we had so much water to begin with and very little of each of these 2 products, proton and hydroxide. This Keq is very small because the numerator is very small. I'd like to describe one more concept, and that is Kw. But to describe Kw, we need to get rid of all of this equilibrium business. Kw refers to the ion product of water. The W is for water. So we could write this Kw equals proton concentration times hydroxide concentration. I think you can see that Kw is related to Keq because Keq times the concentration of water equals the concentration of hydrogen ions times the concentration of hydroxide ions. Okay? Keq times concentration of water equals the concentration of the products. So we can just substitute Kw right here for Keq times the concentration of water. And this is possible because remember how small Keq is. The concentration of water is actually pretty fixed. It's not really affected by these concentrations of protons and hydroxide ions. So let's just define Kw, the ion constant of water, and we'll care about only these ion products and not the original concentration of water. Well, again, this is easy to solve. We know the concentration of hydroxide ions and protons at standard temperature and pressure, and that's negative 10 to the 7th moles per liter. So Kw is equal to 10 to the negative 14th moles per liter squared. This is a constant. This value is a constant at standard temperature and pressure, so at 25 degrees C. All right, we've got this constant Kw. Let's put a P in front of it. That is, let's take the negative log of this. So P Kw equals the negative log of 10 to the minus 14. The pKw then is 14. Let's not stop with pKw. What's pH? Well, pH is going to be the negative log of the concentration of protons. We know that that's saying take the negative log of 10 to the minus 7th moles per liter, which is 7. The pH of regular old water is 7. The concentration of hydrogen ions in regular old water is 10 to the minus 7th molar. The pH is 7. We can also take the pOH. We need to take the negative log of the hydroxide ion concentration, which is the negative log of 10 to minus 7th molar. That's also equal to 7. The moral of the story here is that pKw equals pH plus pOH, and pH plus pOH always sum to 14. I want us to think about how pH relates to proton concentration one more time. Remember we said the concentration of protons in pure water is going to be 0.00000001 molar. Okay? Also known as 10 to the minus 7th molar. Well, if we added more protons, if we increased the concentration to 0.000001 molar, that would be 10 to the minus 6 molar. If we took the negative log of that, we would get 6. Okay, so a smaller pH corresponds with a higher concentration of protons. Lower pH means higher concentration of protons, means more acidic. Since pH and pOH always sum to 14, we don't need to measure both of them. If we know one, we can infer the other. And for biochemical and medical purposes, we measure pH to tell us how many hydrogen ions are present in a solution, in the body, in the blood. And we do that on a scale of 1 to 14, thanks to Keq and its relationship to Kw, the constant ion product of water. The last thing I'd like to show you is how to solve a question like if the hydrogen ion or if the proton concentration is 2.5 times 10 to the minus 4th molar in solution, what is the concentration of hydroxide ions? So we're going to be looking at pH and pOH, and remember the two of them always sum to 14. Remember, Kw is equal to 10 to the minus 14, which is equal to the concentration of protons times the concentration of hydroxide. We can fill in half of this equation. So 10 to the minus 14 equals 2.5 times 10 to the minus 4 molar. This is molar squared. And the only unknown left in our equation is the concentration of OH. You can do some simple division on your calculator and solve that OH minus concentration. Hydroxide concentration will be 4 times 10 to the minus 9 molarity. If you know proton ion concentration, you can calculate hydroxide ion concentration. This is what the Kw does for us.